Cool. So, hi everyone. I'm Claassens Jim Hill. Thanks, Paul, for letting us give a little talk here. Kind of pick your brains a little bit on some interesting things that we're a little bit passionate about. We're from NavAbility. And at NavAbility, we're looking at robotics, specifically like data management and navigation of robotics. So really the tagline is navigation software simplified. That's a big topic. Jim, can you go to the next slide, quick? Let's hop into what that means, quick. So yeah, I'm sure this cannot be a surprise to anyone, especially for devs, no one in the room that's done robotics, right? We've all heard about, was it Arthur Clarke? Some major author said AI is always 20 years away. Robotics kind of feels the same thing. It's always great in a lab, and the moment you want to leave the lab and put it in a real world, things fall apart. Talk about self-driving, and every Jetsons-like dream we've ever had has always been kind of like shattered as soon as the investor money runs out. It's a difficult challenge. Kind of recreating things to work in our chaotic space is hard. We've seen that a lot. So this cannot be news to anyone. We're looking at how to like make robots work in real space. Jim, can you go to the next slide? So boiling it down to the most simplest case possible. And I'm going to bring this back to GraphQL in a few minutes, but we want to start with really what the context is. You generate a lot of data as a user, as a human. You generate a lot of information, a lot of that's potentially related in graphs. Robots do very similar things. In the most trivial case, you have a little underwater robot we've got here. It's using, you may have heard the term a LiDAR or a radar. It's processing camera data, and it has maybe compasses or gyroscopes that it's using. Streaming this information kind of all the time. The most trivial example of a robot like that is your cell phone. So we're actually like, when we have to boil this down to something that makes sense, the easiest example we ever use when we're talking to like investors and stuff is a cell phone. So I want to use the camera on a cell phone, and I want to use the compasses on the cell phone, and I want to localize the cell phone in space, and I want to do something with the cell phone, right? And that's a lot of data to process. So effectively, if you can go to the next slide, Jim. Thank you. What you need to do at the end of the day, to be able to make your robot or your cell phone effective, is you need to be able to put it in somewhere in space. You need to know where it is in space. And we as humans do this all the time, right? You wake up in the morning, for good or for bad, and you look around your room and you recognize where you are, right? If you wake up in a strange room, or you wake up before a bar, you're like, okay, hold on, what's going on? And you can kind of put yourself in space and time. Robots need to do the same thing. They need to do this massively effectively. And that's a big problem, because talk about crunching gigabytes of data from camera processing information, or from like LiDAR scans, or from gyroscopes. Ideally, putting all of that together as well as a human does, and being able to pull a map out, that's a very hard problem to solve. Jim, can you go to the next slide, please? So we're looking at this as a problem statement. There's a lot of research done on these things, but we want to like productionize this. And this came into really a number of technical challenges. Specifically, how do we transmit the sensor data from a robot on the edge, maybe a phone? You can't do that much work on this thing, right? You need to bump it into the cloud and then solve it there. How do you do that really quickly so that you can actually get an answer back while it's still relevant? How do you trigger, once you send the data up, how do you ask this robot or this cloud infrastructure to give you a good answer for a map? That takes time to calculate. And then how do you bring that information back down to the robot so it can use it? In a perfect world, you're doing this actually at 20 hertz, because that's like roughly physical rules. You need to do things as quickly as that. Those are really fast systems. In the cloud side now, how do you store this map? We're not talking about 5 or 6 data points or maybe 5 or 6 images. You're talking, when we discuss this, we talk about what's called the Paris-size graph. It's 10 million nodes, like all the streets of Paris, right? We need to be able to localize something in there, find where you are, pull that information out, send it back to you. So you're processing a massive graph. And then really the part that I'm massively excited about when we originally spoke about this is, how do I query this information? I want to pull out maybe 5 or 6 pieces of information around a specific stop street. Or if I'm looking for my coffee cup with my phone, I want to be able to pull out where my coffee cup is in my room out of, a massive space of 10 million nodes. I need to be able to do that kind of like, we call it temporal spatial queries, but space and time queries, right? I need to be able to do that very effectively. All from this map we saw. These are the challenges we're looking at a little bit. Jim, can you go to the next slide? Thanks, bud. And this gets more and more complicated because one robot's kind of cool, but like a Roomba in a room, right? One is fun, one is neat, one you can do, 2, 3, 4. Shared information is, and I might go a little blue sky research here, but shared data is infinitely more valuable than singular isolated islands of data, right? So Stefan, you're a robot, I'm a robot, William, you're a robot, Jim is a robot, definitely. And if we can share data about the same space we're operating in, then Stefan, you can find my coffee cup. Jim, can help me go get it, right? We can share this information. So shared memory is massively important. It's what make or break Tesla. And it's a rabbit hole we're going to go down, but it's a cool discussion of it though. But the value of relationships across multiple agents or robots or multiple cell phones is incredibly valuable. It's not a linear thing. But there's challenges in solving that. And I'm not going to go down that rabbit hole, but if you have time to ask the questions, I'd love to talk about it. The challenges are, though, how do you build these relationships across multiple robots? How do you share the information between them? And now you're talking about 10 million graphs, right? How do you pull data out of that for like 5 or 6 robots trying to clean a room, or call you want to build a robo mode that's mows your garden, right? And you have 6 robots that are doing this, and each one takes a little piece of territory. How do you do that? How do you share that information and query and pull out like, okay, you go solve that part and I'll solve that part. And then on top of that, well, the question that comes into everyone's mind when you talk about cloud is obviously, how do I integrate security? Because if I can see William's data, William can see my data, Jim is going to freak out, right? Because that means that it's not a commercial solution. These are huge problems, and this is a big discussion. And I'm sorry if there's a little bit of background noise, but this is the context of the problem we're looking at. Why this is coming to a GraphQL discussion is because if you take the robots on the left of the picture and you replace them with people, it's the same problem. It's exactly the same thing. You're producing data, you need to relate it, you need to push it up somewhere, and then you need to be able to relate that information to other people, right? Like the Facebook project. So it's very much the same thing, just think about a lot more information. Can you go to the next slide, please? Thank you. So like in a nutshell, and I can talk to this more, but we've only got 40 minutes. We thought we'd be really quick, and we did the slides, and this is like a discussion we could spend days on. But in a nutshell, it comes down to, how do I persist this data in the cloud? I need to push it up really quickly, save it, cache it if I can, because some of these robots we're looking at are like underwater, where you have a very slow data connection, or they're talking to a satellite, right? So you have high latency. How do I push that data up? How do I let it do its thing? And when it gives me a better answer, how do I make a subscription so I can quickly pull it back? Ideally, I don't want to pull you, right? I don't want to be like, Jim, got a new measurement for me. Stefan, got a new measurement for me. Ideally, when you're good, like the Erlang paradigm, one we've all talked about, how do I raise my hand and say, Solver has a better answer for you? And then obviously the query problem, right? A parasized graph. Now, when I talk about how we solved this the first time, we solved it with wedge layers, and querying became a nightmare. But we want 10 million nodes in a graph. We want to be able to traverse this really quickly, pull out relationships. And that's part of the problem that we want to solve. And lastly, put this in the microservices, because if you're looking at a monolithic way, you're going to build one solution. And this is what the academics are doing right now, right? They build one package or one solution, one box of tricks, and then you kind of try to sell this, right? This is what some of the robotics companies are doing too, in a black box, which is hard, because maybe someone produces a slightly better image processing algorithm. Maybe you put deep learning in and you're pulling out better coffee cups than I am. Like, how do you weld that into the existing graph so you can kind of start consuming information itself and then pushing it back up? Because we want to do that. You want to like fold in slightly better algorithms, right? And you need a microservices paradigm for that. So that's our nutshell. That's basically the robotics problem as we see it. Jim, can you go to the next slide, please? So many moons ago, and by many moons I mean like probably 4 years ago, we solved this problem. So this was an academic paper, and the way we did this is we did it with REST layer. So there's a little robot running. He's doing construction solution. He's trying to. We're processing a lot of, a robot in a building, and we want to. Where should you drill the holes in a room? Because you're building this structure, and as you're building it, I need to say, go and drill a hole there, and drill a hole there, and the robot's going to tell you where to drill those holes. And the way we solve this, which is effectively produce a map, find out where the hole should be, and go and drill the holes. The way we did this with this big REST API. And the way we built the relational map in the background is we did it in Neo4j, because we wanted a graph, right? All the relationships are more important than the data alone. And the way we stuck this very complicated solver algorithm, which everyone calls SLAM, but we have a slightly, well, we think it's a cooler version of SLAM, simultaneous localization mapping algorithm. Think of it like a way to produce a map from disparate data. We used the language Julia to run that and talk to this Neo4j database. And whenever answers came back, we pushed that to Kafka, to the REST layer, and the robot queried it. Like, got a better answer for me? Got a better answer for me? So I hope some of you are cringing a little bit, because there's some holes in this design a little bit. Now, for users to be able to pull answers out of it, we did probably one of the worst things alive, is we exposed like effectively a SQL query that they could run. So users, because we were trying to show how this works, we let them run effectively what's called Cypher queries in Neo4j, but it's legitimately SQL with all of the nightmare problem SQL injection, right? So we're like, okay, users are small user base. We didn't even have authentication. We let them run SQL queries so they could query this information back. So you could run, get information with REST queries, and then when you want to do something really powerful, you can use a SQL query. And I went for a run with Jim. And Jim was like, this is an awful idea. And he's like, let me tell you about this GraphQL thing. And let me tell you a bit about it. And obviously, I am the biggest skeptic of new pieces of technology, because I think, things live and die quickly. And, I don't want to adopt this technology simply because it's cool. So he's like, hang on, let me tell you a bit about it. And I was a hard sell. But he actually built out a PSC of, took this slightly hackish thing we built, and he built a production version of it. And I kind of wanted to lean into this. This is what Jim built from this original problem statement that we had. So I think, Jim, that's probably a good portion for you to take over.
Oh, were you going to go through this one? Or did you kind of go through it?
Oh.
Kind of talked about it a little bit.
Oh, even better. Okay, yeah. Oh, yeah, okay. I think I may have talked over it quickly, but yes, there were massive problems with that structure. And I'm sure if you've worked with GraphQL a little bit, you would know these things, right? Popping up. Like, it's incredibly slow. Actually, the robot was in South Africa, and I was solving technology within Virginia. And it was fairly unusual, obviously. Because you would go, because it was like, you would have to go /robots, get a robot, / sessions, get a session, / new data, get new data. So there's this N+1 problem that just made these queries really hard. We couldn't filter the data down, right? You got kind of the whole thing back, you got nothing. Obviously, users writing DB queries directly is probably not the greatest thing to build. And then no authentication, authorization, no auth N or C, and no subscriptions. And I was talking about building a web socket to do subscriptions, like the way GitHub did their web pages. Because effectively, I wouldn't the server to tell you when things have changed, and I don't want to be able to pull a system and just make the situation far worse. So that was the hacky thing that was in place. Then came
GraphQL to the rescue. So, we had talked about these problems, and, we decided to build a little architecture, which we call streaming CQRS. For anyone that's not familiar with CQRS, it stands for command query something segregation. But the idea is, for anyone that's familiar with GraphQL, like, mutations are completely separated from queries. So commands are things you want the server to do, and queries are data that the server has. And you want to segregate those two things. So, the first thing we wanted to do was we wanted to start getting into this microservices space. So, we had that Julia solver. It was running Julia code. Julia is a pretty new language. It wasn't even version 1 when we started building this. So we wanted to sort of isolate that and abstract that. So we wanted to build an API in front of it, because without the API, then you have to do a lot of low-level programming to make sure that Julia talks to, JavaScript, which is what we're writing other things in, right? Which gets difficult because now you're building like transport layers over sockets, like actual computer sockets and things. So it's not great. So what we used is this little Diana package, which built a GraphQL API for our solver. And I'll go into more detail on that. The next thing that we built was we actually had that sort of graph. We call it a vector graph, but it's a graph in the Neo4j. And we had that database. We already had it, and we had data in it. But likewise, we wanted to abstract it. So we went looking for technologies to build an API in front, and we found this little Neo4j GraphQL library, which basically can talk to Neo4j directly and produce a GraphQL server layer for you automatically. So we'll talk about that as well. And then, the next piece of the puzzle is had that Kafka layer, which I refer to as event broker. It's basically just an event stream. It just holds on to events. And that Kafka layer, we had processors processing it, but it was talking directly to database. So you see this upper arrow, it was talking directly to the database. So then anytime we wanted to change the database, we had this sort of coupling. So, what we're working on now is making those processors talk to the API so that we can change the underlying data structure. We could change the database. We can do a lot of things with the database and not have to change that API layer. But then how do we actually wrap this up and produce an API for our customers, right? And that's where we used Apollo Server. So basically we use this idea of stitching these back-end APIs together using GraphQL tools to get a nice stitched query layer that's completely segregated from our mutation and subscription layer. So you'll notice these back-end APIs don't do mutations. They're mainly for querying. The event processor calls the mutations on the database API, but the users can't call mutations. And that really helps because now we've decoupled our uploaded data, because like we said, robots, they're like streaming data, right? 20 hertz, it's just data, 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 data. So you don't really want to do the request response thing. You don't want to do HTTP. You don't want to have to do an SSL connection every single time. So with this strategy, we can just open a WebSocket and stream data into the event layer. And then it all sort of happens eventually. And then on the other side, we've segregated for the query. So I'm going to go into great detail about these sort of 4 technologies that we used to solve a lot of these problems. And then obviously the last bit is now that we had an API, those clients, the people, the app, the robots, they have a single interface layer that they can interact with. And they don't have to worry about writing Neo4j queries because, they don't have any idea. It's like 2 layers of abstraction away. And that's just a consistent API layer, which gives us the flexibility now to scale and change our microservices. If we wanted to add, a feature for calibrating cameras, we could build a camera calibration microservice and stitch it into our API gateway. So this gives us the ultimate flexibility in user experience while also enabling multi-language and flexible backends. So I'm going to quickly go through those technologies I talked about and kind of why we selected them before we go into sort of the demo phase. So for the solver API, right, our solver was written in a language called Julia. In our company's opinion, it's the most powerful language in existence for doing any sort of scientific iteration. So there's a couple of different options, right? There's schema stitching. So in 2 slides, I'm going to talk about schema stitching. So I'll answer the question for federation in a couple of slides. So for sure. So sorry, back to Diana. So Julia is a really powerful language, and we wanted to be able to just surface our Julia code really quickly, but it's also a young language. So we wanted to abstract it. And we found this library, Diana. It enabled us to integrate quickly. So if you're looking for best-in-class Julia server, it's Diana. And there's also 2 options for client libraries. So this very young language, Julia, still had support for GraphQL, which was great because it didn't have support for lots of other technologies that might not be so ubiquitous. So moving on. So the database API, this is the Neo4j GraphQL, and we actually used it when it was the open project, and now it's properly maintained by Neo4j. Actually recently migrated it to the official release. But what it does is it provides schema first integration with Neo4j, which is super nice in that we already had data in the database, and all we had to do was write a little GraphQL schema and it'll connect. So for example, we already had in our Neo4j database relationships between robots and sessions. I don't know if you can see the pointer, but the second code is, and you can see how there's sessions. And in the big yellow where it says relationship directive, there's just this really simple GraphQL directive for representing this graph relationship. So it's a very declarative way of just saying, hey, give me this relationship. If a more complex relationship, you can write your custom cipher here, which you see on the bottom. And that's great because, you know, Neo4j is a proper graph database, right? GraphQL it's sort of in between REST and a graph database, right? It doesn't have all the power of a graph database. It's more like a directed sort of graph representation. So, you know, if you are sort of new to GraphQL, you know, graph query language is technically a full graph query language, whereas GraphQL is more designed for like it's sort of in between. It's better than REST, but it doesn't have a full query syntax. So we can use this custom cipher to sort of bring that, which is really nice. But now the only people writing custom cipher is the developers that are right next to the Neo4j, right? So you can have a Neo4j developer, also known as Sam Claassens over there, do this without everyone in your organization having to know cipher. And currently in the graph world, there's a couple different graph query languages. It's not totally clear which one's going to win the day. So it's good to have that abstracted. The key thing is we wrote 0 custom resolvers, and we were able to leverage all of our existing data, which is just incredible. We just wrote a schema, plugged in the plugin, and boom, we had a server that worked. It was amazing. So I really appreciate schema first type things. And we're also able to use our existing auth-n, because as you can see up there, so you can see where it says auth at the top, right? You can just pass in your JWT token directly into your header, just like you would anything. And the framework has a way to read it and understand it, and you can just use it in your auth. So we didn't have to change. We're using AWS Cognito. We didn't have to change anything. We could continue to use our JWTs. The framework didn't define how we did our auth-n, but it did give us the ability to add auth-z. So if you look at GraphQL's best practices, they often say, do your auth-z as close to the microservice as possible, do your auth-n way out the front end. So that's the pattern that we're using. So stitched query API. So in the stitched world, right? So I really, I personally have a preference for schema first. So I really like the way that the GraphQL tools has gone through and designed this. So it's a very schema first way of thinking about it. So we can take our schemas either through introspection or through, if you had a package with all your schemas in it, you could do it with introspection. We like introspection because it sort of builds a native health check. But the GraphQL tools is pretty powerful in that you can take all these transforms. So the Neo4j framework made choices for us, and we already had data in the database. And we had chosen to name it capital USER, all caps. But what our experience was, is we wanted our customer experience to be U, lowercase s, lowercase e, lowercase r. So we were able to do a little rename transformation without having to change our database schema, which was really powerful in that now we can have our backends be sort of independently developed. We have this way to filter and transform and produce the customer-facing experience that we want, even though the backend might change at different times. And the flexibility to use that sort of really opinionated framework, right? That Neo4j framework is really opinionated. but with schema stitching and these transformations, we're able to change the way that it appears in our user experience so that we can be opinionated about how we use it. So federation. So there's sort of two ways to handle this. And I'm going to say nothing bad about federation, right? Other than when I was first learning this, I kind of just went down a path, right? And so I chose GraphQL schema stitching, schema first. It's open source, it's free. There's definitely other options for doing this back-end stitching, and federation is definitely one. I don't personally know enough about it to be an expert, so I'm not going to say a bad thing about federation. But there's sort of a couple different ways to do it, and we've selected to use GraphQL tools, which is schema first, sort of change your schema and make it executable. My understanding of federation is you kind of do that more on the resolver side, but I might be wrong about that. So yeah, I think federation is probably better. It was a little bit more complicated, but maybe that's a conversation for someone else in another talk. I would love to see, schema stitching versus federation, pros and cons, right? I'd love that. But we've chosen schema stitching. I think the moral of the story for stitching versus federation is you want to do one of them, right? You want to design your system so that you can have your user experience decoupled from your microservices. So don't try to just build everything in one layer and then have to change everything every time you change anything. So I think there's, both choices are good. It's just a matter of, what your particular use cases are. And maybe someday we'll find the gaps in schema and have to change, but here we are today. Cool. And then moving on. So we had that gateway, and we basically, we needed a subscription server and a query mutation server running at the same time. So Apollo server is really great for this. Just sort of drop your subscription server in an Express app, and then a separate query mutation server in the same Express app. And there you go. So one of the things that's really nice is this supports both WebSocket and HTTP. So right now we're HTTP, but we're working really quickly toward making this full WebSocket enabled to solve our, high frequency data push problem. And yeah. The last thing I didn't really talk about in the clients that is really important for us is we wanted all of our clients to be able to be offline, right? So our app is actually a PWA, so you can download it and use it offline, connect it to a robot, whatever. And we use this little thing called a Persister so that every time you make a GraphQL mutation, it saves it to the Persister and then pushes it into the network layer. And the value of that is if you lose the internet connection, your robot doesn't stop driving. It can still do its job. It can still gather data. And then when the internet connection comes back, it will push all that data up. And because we did command query segregation, you'll get all those events incredibly fast. Now, it might take a little bit of time for the cloud to process it, but if you lose internet again, it's all up there because it should be very, very fast over a WebSocket to just put everything up there. So having this ability to go offline and update only when you're connected is really powerful for our poor connectivity and high latency environments. Yeah, there's I love that Darius is chiming in because there's so much going on in the schema stitching and federation space. This is like the cutting, like when GraphQL first came out, everyone was like, well, how do we do this? And now there's a bunch of people solving it. So I love the thought leadership on that. Thank you so much. Cool. Now we're going to jump into a demo. Sam, do you want to give this a try, or do you want me to do the demo?
Let me give it a kick. We'll make it fairly short so we can take some time for questions. And as to your Persister strategy and your caching, I was driving up, and as I was driving between Sheboygan and Green Bay this afternoon, I was spotting internet, and I was actually watching that work. So I don't know if anyone's QA tested it, but I did on the way here. So just a heads up.
Awesome.
Yeah. Yeah, please let me know if you can see my screen in a second, and then I'll make this fairly short. because I like
Looks
the
good,
discussion
Sam.
that's going on in the chat. So I think, okay. So demo. So as we spoke about, right? Robots are pushing a bunch of data up into the cloud or like locally, right? So we're going to push a quick example data set. I'm going to show you a little bit of the web app side, a lot of the marketing side, but just to kind of show you really what changed and where the GraphQL is plugged in. And I'm going to hop into the GraphQL side just to show you what the structure and the schema looks like. And just something fun, I might quickly at the last second walk through the SDKs. And the only reason I'm going to do that is because I want to show you something that we were excited about, which is all of our workhorse work. Well, I'm seeing the thunder. Sure, let's do it anyway. All of the workhorse stuff happens inside a common set of queries. So we can write one set of queries and then fork it out to 2 or 3 different languages. And that was very exciting for us. So I'll come back to that in a second. I kind of didn't say that. Okay, so step 1. So we're now in our web app, right? This is an NavAbility client. There's a whole getting started example, but I'm going to skip ahead and just go to our experiment page. Now I'm already signed in, so I'm a test user. Just make sure I can see everything already. Cool. Okay, so what we have is like a lot of people doing demos and doing testing stuff. We found out that they don't have a robot lying around in their apartment, which is really surprising, because I'm sure everyone on the call here does, because I'm sure everyone like teach out the way we do. But one of the examples is just push the test section up. So this is a quick, like, simple piece of data we're going to push into the cloud. So what you'll see is that that's a one-click mutation, pushes a bunch of data. The exciting bit about that is the subscription that's going on over here on the right. So the toasters are wired up to a subscription. So we pushed up a little piece of data. Actually, I'm not going to do it here. I'm going to hop to let's draw in the topology. So you're going to see the data as it's pushing up. Now, I wish I could have shown you the REST version of this because, well, this is a dumpster fire. I mean, because you want to do this and there's something querying continuously for like, oh, more data. Do you have more data? Draw more information. Here, the subscription, it's polling, but also there's a subscription going on. We pushed a lot of data very quickly. And as it's solving and connecting the data, and remember we spoke about like as a robot's driving, it's connecting the dots. Well, you're actually seeing the dots connect. And the fun part when I saw this the first time, that was like fascinating, is I could like dig in. I peek at the response obviously, but the request is what interested me, is the queries, right? This is just one query to get all of this information. So remember we spoke about there's multiple users, there's multiple robots, and every robot has a session. Well, you may have not mentioned the sessions, but we don't want to go too deep into the robotics side. If we have a minute, we can chat about that. But consider multiple robots, right? You want all data for all robots. And you can write one query that gives you everything from how many robots in the room all the way through to how much data is there per robot. And the part that was kind of blew my mind when I saw this the first time was it's one query. In GQL, in REST, it was like, give me all robots, give me their names, go ask everyone for their data. And you had built 14 queries before, or 14 REST calls before you could even draw a picture, which was fairly bad. I actually have the other framework here. I opened up while we were chatting to see it. So this is the part that really like I got excited about. And in parallel, you can see the subscriptions running. So now I can go do some extra work. I'm now going to ask, remember we said we can let it solve a graph? Well, I can click solve here and it'll fire up a mutation. And I'm actually watching the subscription. Now solve takes a few seconds. And as it does, I can hang around, I can go see the data. I can also like draw the data as it's coming back and then see the solve as it happens. Now it won't happen here. I'm not going to do it right now, but there's a spatial map. Remember we said like a robot in a map in a room? Well, as the solve comes back, I can see this data. So that was very like quite neat. So when the subscription hits, I will suddenly see a new map that opens up here. I'm not going to wait for the cake to bake, as they always do. I'm just going to hop a little bit ahead because we're talking through. We want to dig to the GraphQL at the end of the day. So that's roughly the web app structure, and this is completely redesigned with like one unified schema on the back end, and that's all in GraphQL. And like personally, as a user of it, it was very exciting. On top of that, if you go to the API, So this is app. It's now API.d1. You can go, we have Apollo server running with Playground. You can kind of play here. So this is where I spend a lot of my time. Originally was writing Neo4j queries. Now I spend my time running GQL queries. I'm quite happy about that. It's infinitely better for me. I don't have to write match this, where this relation is. I just have one schema that's running. So a simple, the cleanest simple example here is give me the user guest and give me all robots that guest owns. Remember, because a user owns robots and robots own sessions. That's how the data is structured. And this is throughout the whole application. Can you still see my screen?
Yep, we can see it, Tim.
Okay, great. The network just shut down for a second. How much time do I comfortably have to dig into this?
We can still hear that.
Okay, I've got okay, fantastic. I've got 3 or 4 minutes. I just want to quickly shoot through this. So remember, like, I was writing out the equivalent REST commands that I was running before that, would fly from South Africa to our servers and then come back so the guy could draw a picture so he could show a client. I was writing out those queries and they were like fairly difficult. Because remember, we want to filter by timestamp. We want to filter by like location. The part that kind of worked was really cool for me was I could write this, run one query, get a list of all my robots, and be like, okay, cool. From here, I can get all sessions for the robot named Feb2022, right? And of all the
Shameless,
sessions, I want all the data related to
2022.
Oh my gosh, yeah. If I can type, obviously I can't type, so we're not going to do that again. There we go. Okay, so now I'm digging it. The cool thing that when I saw this and I was using it, and I'm sure you've done a lot more GraphQL than I have. What I loved about this was I could incrementally grow my data set. Remember, I said originally I had to return everything and then filter down to what I cared about. Here, I just simply give me the label of all the data in the scene. And this is worked out perfectly. And then you can do really fancy things. Like this is the most trivial example alive, but because GraphQL lets you index by position, I don't remember the name of it. Anyway, I'll come back to it. You can index by position, or you can index by time in Neo4j. You can bubble that up. So you can say, give me all data around a specific location, around a specific piece of time. So when you're doing a 10 million graph query, 10 million node query, it becomes super easy. And I don't have to do anything fancy on the GraphQL side. That's all kind of just baked in, which is very, very neat. So I'm not going to go too deep into this. I'm sure I'm preaching to the choir about GraphQL, but I thought this is one of my interesting takeaways. I was able to use it this way, develop this way. I'll show one last thing quickly, and then we can have a quick chat. But we have a bunch of SDKs, obviously, because we're supporting users viewing through the API, but really what we want to support is people building robots. A lot of people are using ROS and robotic operating systems, and our clients are truly robots. Users are the person paying the bills, right? But our users are robots, which is the funny part. So we want to support a bunch of SDKs depending on whatever language you're using, which is a problem because I don't want to support 3 or 4 different SDKs. And Jim came and said, look, let's bake the queries we're going to use, and we write them once, and then we share them between the SDKs and make the queries the workhorse. So if I go and open the Python SDK, for example, right, it's a very thin layer, just auth, effectively. And then you get back the GraphQL client, and all of the work is asking the right questions, which is through the GraphQL layer, right? So you'll see we've written one common set of queries. For good or for bad, they're a little complicated. Maybe we can make them better. Probably can make them better. Hopefully, you're not looking at this and considering that. Oh, I remember my first query I wrote. But if you are, that's great. Let's chat about it. But these are the workhorses, right? So all of these are common sets of queries we write once, and then each SDK simply just uses it to ask the right question. So, give me all robots or go and do a solve is simply just asking the right question. Route this mutation, go and call a solve session. And that's what it bubbles down to. So that was really neat to me. But just think about like dollar per code work I have to do to keep this thing alive. If I want to introduce a new language, someone says code this up in Rust. I have to like think about, oh my gosh, now I need to go and spend a whole bunch of time writing boilerplate code as we did in the past. This is the GraphQL equivalent. Back in the day, we called it graph. Like this is the REST equivalent. And all of it was just building the right URLs, which is a nightmare. Right? I wanted the right payload. I didn't care about where the endpoint was. And that's what it gave me. So I could just, writing a new SDK in another language, super easy. So from the top down, that's producing a bit of data. We can push into the cloud. We can draw it. All of that comes down to really putting the right queries together in the Graph API, and we're building like easy SDKs from this. And these are super beta. I think beta. We're using the word beta liberally. I would say take a step back, call them alphas for now. They're good, but they're getting there. So like. So yeah, that's our version 2.0 solution as right now, to be able to solve this kind of problem. And
I'm going to go ahead and steal the sharing back. Yep.
Yeah, go for it.
So the last slide, everyone. I just kind of wanted to summarize some of the thoughts and lessons that we haven't already talked about. And first, Julia needs more support. So if you want to be a part of the Julia's growth, right, we're looking for people that love Julia and know Julia and want to really support a GraphQL server for Julia, because I think that would be a really powerful thing for the scientific community. One of the other lessons is out-of-the-box tools are great because you can go to market really quick, but consider where they're limiting user experience, right? So try to understand that a little bit before you choose a tool. So we talked a little bit about federation versus schema stitching. Those are out-of-the-box tools. They help solve problems, but with every tool there is pros and cons. So consider that one looking at them. Schema stitching is really powerful, but as some people have pointed out, right, it does require a bit more understanding of how the server engines work. So you might want to consider just using a provider for this. So we started this a couple of years ago, but now there are so many providers out there for helping you to produce that nice customer experience, that customer API. By doing the abstraction for you. And I actually believe that the WonderGraph guy is one of these providers. So I'm really excited to see what, he's going to basically tell me everything that I just said is not needed, because his product is awesome. And I'm sure it is. So I took a quick look at it before he came. So definitely 100% consider a provider, because even though, we talked through it, don't bake your own if a provider solves your problems. So we have a bit of a unique situation with the streaming CQRS. So that's why we choose not to do a provider. But for most use cases, go find a provider to solve these problems. And decouple your auth N from your auth Z. And then distributed context is hard, because you do have to pass that auth through. And you do need to make sure you understand that for like tracing and all these kinds of things. But it is easier with GraphQL than a lot of the other ecosystems. So thank you, everyone, for listening to our talk. Sorry if we rambled a little bit much, but if you have questions or advice, put them in the chat, talk now. And if you're out of time and you want to talk to me more one-on-one, come to our YouTube channel. We do office hours every other week. So thanks, everyone.